Hello and welcome to 8th lecture of the course on corrosion, environmental degradation and surface engineering. Topic of this lecture is surface degradation mechanism due to heat or radiation action. Now, I can say also heat and radiation action, but we know very well that heat itself can damage the surface, radiation alone can damage the surface, and of course, heat and radiation both can damage the surface. So, that is why the title has been kept as a surface degradation mechanism due to heat or radiation action. There are three main phenomena in that. It may have a completely temperature, may be related to photochemical or somewhat high energy radiations. The first question comes, why do we study this topic at all? Is there any need? Yeah, there is a need. Reason being the radiation and heat have a wide variety of effect on the materials, from simple heating to the radiation induced deterioration. Heat alters the physical and chemical properties of material. Radiation can produce faults in a material's atomic and molecular structure, which can add up over the time and lead to the material failure. There are many ways in which material can deteriorate when exposed to heat or radiation. This lecture is meant to help students understand those processes. Again, this is not a detailed lecture, it is only one lecture we are focusing. There will be a number of references, there are books available. If you are interested, you can deal or maybe you can refer those books also. But our aim is to introduce the topic. Now, let us start with this lecture. What has been mentioned here, heat is a way you say the word heat or radiation, or I can say heat plus radiation also, right. So, there will be total three kind of the failure mechanisms. Now, individually I am using the word thermal heating, individually we are using this in this case is the UV or any other radiation. UV is one of the very common available, maybe we have a good understanding about the UV. So, starting with thermal heating, we know it is going to change a microstructure, and we will cover a couple of examples and indicate even simple to simple examples which we have already covered. We are trying to highlight or we are trying to review those examples and indicate yes how the thermal heating is changing the microstructure. Now, microstructure or change can be grain related, it can be grain deterioration, grain growth, it can recrystallize the metal, maybe one form to other form, and there is also possibility of the phase transformation, it can be a melting also, which we have studied in one of the previous lecture. Coming to the sun or UV or another kind of radiation, it can cause a localized heating. Now, this localized heating can cause a damage to atomic and molecular structure, it can cause a melting also, or in third one is we are saying that maybe the kind of some atoms are getting migrated from one surface to other surface. So, what we say radiation induced atom escaping, and this is the locally degradation. It may form the cavities, it may lead to the cracking, or in some cases swelling also is a possible. So, these are the some phenomena. If I want to present these words in a different manner, what will be that? It is a damage to atomic and molecular structure cause changes in a mechanical, physical and chemical surface properties. Formation of the cavities lead to the surface degradation, some material become a brittle. So, we will cover a couple of examples on the conversion from a ductile to brittle failure. Metal exposed to the radiation experience migration of the atoms from inside the surface also. We say within a surface there is a possibility of the atom migration, resulting in a reduced ductility, reduced toughness and finally leading to the cracking. In few cases, radiation exposure displaces atoms and rearrange those atoms also. That means we have intended something, we have designed some surface in some manner, and because of exposure of the radiation, exposure to the heat, these atoms are getting changed, and it happens most commonly in the polymers, and in some cases in the kind of the rods which we use, and then the swelling occurs in this case because of the rearrangement of atoms. As a result, surface may inflate because of the swelling, and I guess given that some sort of the rod is often example has been cited as a nuclear fuel rods, they generally fail due to the swelling. Another one, as I mentioned, the melting. I can say the melting is one of the most severe type of surface damage, which we have also covered in previous lecture. It should be avoided. In that lecture also I mentioned very clearly, it should be avoided as much as possible to limit the temperature rise. If you find that it is because of the circumstances, the temperature rise is going on the higher side, we should make some arrangement for the cooling, and the cooling system must be employed, must be established to reduce the temperature. Now, let us see some sort of a heating effect on a microstructure. We see the effect of heating on a microstructure, and then we are showing a diagram, the figure 1, A, B, C and D. Now, here the some terminology MGB, PAGB and martensite packet has been mentioned. So, there is a need to expand or maybe say that give a meaning of that. We say the GB stand for the granule bainite, M stand for the martensite, Ma is a martensite austenite constitute, and P, this is the grain boundary, PAGB is a prior austenite grain boundary. And most of the steel cases, this PAGB is a very common, martensite is a common, and bainite is also common. So, we are trying to cover this we say the nomenclature in this kind of a microstructure. You are able to see that this kind of the grain boundary here that shown as the red color points. Similarly, there is a martensite boundary in this case. This micrograph is the 40 micron, but we zoom it, then we are able to see some sort of boundaries very clearly over here, and then some sort of what you say the martensite austenite structure also. So, these are the grain boundaries and maybe some sort of discontinuities in a material, and then indicates what are the constituent of that, whether the martensite is going to dominate. If a martensite gets a domination, then naturally the brittleness will increase. However, if the bainite is going to increase in the content or the matrix form, then the ductility will increase. So, that is what has been shown. And now, what is the really reason for changing from bainite to the martensite? We see generally we do after austenite, we try to go ahead with the heat treatment, because austenite will not have a lot of hardness. We do a normalization or a normalizing, maybe say air cooling, or we do a quenching also. So, there are two processes, A and B are related to normalizing, and C and D are related to quenching. In case of the quenching, we are finding the matrix of the martensite in a greater detail, and even in this case the PAG is also, the PAGB is also there, but this one PAGB contain maybe say 1, 2, 3 or 3 to 4 martensite packets. So, naturally the hardness of the martensite will be on a higher side, but they will have a much more chances of the failure. How do we get this? Generally we go ahead with prediction well in advance using the CCT curve, that is a continuous cooling transformation curve. What does this indicates? It indicates what is the cooling rate. Now, if there is a temperature increase, maybe say 800 plus, and we want to now cool it. If the temperature is the decrease is very slow, then the most of the austenite phase will remain there, ferrite will be in a good shape, and then there will be ductile the phase, or maybe say failure will be ductile failure if it is subjected to very heavy load. So, 0.1 degree centigrade per second. Now, coming to the water cooling, what we go ahead with 100 degrees centigrade per second or more than that. While in this particular microstructure which has been taken in this case is roughly 340.5 degree per second quenching effect under the heat reduction, or we say that the cooling is done in a manner so the temperature comes down immediately or instantaneously. So, this is a changing the complete microstructure. Basic material is same, still there is the same base material, but because of the normalizing heat treatment procedure, we are finding the structure is somewhat different. In case of the A, we are finding the some sort of the bainite formation, and in the case of the C and D, martensite is in the domination. If you want to express in the other word, or maybe think in other word, what do we say? That is the prior austenite grain boundary, that is the PAGB, is important for understanding the microstructure scale of mechanical properties, because PAGB, if you are able to see, you can really predict what will be the mechanical properties, what kind of the strength will be there, ductility, fracture toughness, etc. And we also can predict the surface hardness. So, this is important to understand what is a PAGB, and as I say, in most of the steel cases it has been considered significant manner. Now, coming to the normalized sample, we say that in granular bainite was the dominating, we say the GB microstructure with some sort of martensite, maybe the lesser than 5% we generally observe in this case. And then if you look at the grain size, it will be roughly 25 microns. It is slightly bigger than martensite, because martensite micro, if they say that the grain size will be roughly 24 microns. However, in this case also, in the granular bainite also, we will find some sort of martensite austenite constituent, but generally the sizes are very small, it is like a lesser than 1 micron, and they remain uniformly distributed. And then one main thing, particularly in granular bainite, is missing of the carbides, and that's a main. Otherwise, in martensite we find the many carbides. So, in this case, carbide largely remain absent. In quench sample, in a water quenching sample, what we find that the matrix is entirely martensite or martensitic, and with a slight reduced grain size, maybe say as a 24 micron as I mentioned, and then even the PAGB, which is the grain boundary, will be consisting of 3 to 4 martensite packets. We also indicated some sort of curve, what will we use the word, a continuous cooling transformation curve, in that shows a comparison of water cooling versus air cooling, and the air cooling is almost a 10 degree per second, while in water cooling it was around something like a 340 degree per second. And what we indicated in the curve particularly is that the water cooling produces a totally martensite microstructure due to high cooling rates, and air cooling is resulting on a creation of granular bainite structure, and that is GB structure, and martensite formed after quenching has a several dislocation. Another point is that there will be several dislocations, and that will give a chances of the brittle fracture. So, because of the dislocation, and there is more chances of brittle failure. The question comes, so what do we do? Again we go with a thermal treatment, we go ahead with a change in the temperature, and that what we use a water tempering. We do a tempering. So, let us see that what is the effect of the tempering, which is effect of the tempering on material microstructure. So, earlier we did a water cooling and air cooling. Now, here both the cases, martensite and then maybe after water cooling or after air cooling, we are going to follow the same tempering procedure, whether there is a refinement of microstructure or not. This is what our aim is to understand whether temperature is going to change the microstructure significantly or not. So, that is what has been mentioned here. Now, we have already described PAGB in the prior slide, that was a prior austenite grain boundary. However, the two new terms are coming, NT and QT. That is what we said, NT is a normalized and tempered, normalized and tempered, and QT stand for the quenched and tempered. So, NT and QT will be utilizing in this graph, and in this graph micrograph A and B are related to the NT, and then C and D are related to the QT. And what we are able to see in this case, after tempering, we are able to see some sort of the bulged boundaries and straight boundaries. And another one is that here the precipitation starts, a carbide precipitation is also there, and this is what as with zoom has been shown, that here we are able to find coarse precipitation and then fine precipitation, but however the density of the these carbides are much lower compared to the martensite. That is here their density is very high, and moreover here in this case we are finding the coarse precipitates, while in this case is the only the fine precipitates. We do not have a coarse one. So, naturally again the hardness of this structure will be on higher side compared to this structure. There is a because of this tampering, as we mentioned, that there will be formation of the carbides, and then it will be involved with some sort of the boundary or maybe on the boundary. So, that will change the microstructure, that will change the behavior of the surface. So, what we can say here, the ferrite matrix, which is dominating in the case of the benite structure. So, ferrite matrix with a straight and bulge boundary can be seen in this case, as I say, the bulge boundaries here and then straight boundaries. And this is a magnified, because this is a 5 micron, this is a 20 micron. So, this is a magnified, and then further we are taking this as a sample and further we are magnifying it. So, with the magnified image shows a coarse carbide precipitation near the grain boundaries and fine precipitates throughout the matrix. However, there again they are not available in abundance. We will find much lesser density of this fine precipitates compared to the QT sample. Coming to the QT, the sample we say the ferrite matrix and carbides which are dominant in this. Carbide form the spherical discontinuities, there are some sort of the discontinuities will be available in this case and at the grain boundaries, and many more carbides compared to the anti samples, right. So, that is why we say that most of the time QT related sample which is the quenched and tempered will have a higher hardness compared to this. Now, if I want to really and then the thing from a property point of view, we should compare the properties. So, what we are saying, the effect of the tempering on material properties, this graph has been shown strain versus stress, and then we are indicating that strain in this case particularly this is the in the blue color is a QT, that we are able to see it is able to sustain higher stress. That means, naturally the strength of a QT is on higher side compared to the NT, but elongation of the NT is on a higher side compared to the QT. Elongation can go up to this level, maybe say if you see the proportional limit, that is a different thing, but otherwise it can be elongated maybe to 7 to 8%, while this can be elongated to up to 15%, or maybe if you look at this way, then we can say it may be then more than 10%. However, in both the cases, both the tempering cases, we are losing some sort of elongation, reason being the austenite structure which was a basic, and then we did after that the heat treatment and the thermal treatment on that. That is that generally has a elongation up to 30%, and that is on much higher side compared to the benite or compared to the NT or compared to the QT in this case. Now, if we try to express in the words, we say microstructure of anti sample is predominantly made of the ferrite matrix and precipitates phases. However, as we mentioned that in this case there will be coarse and then the fine together, and then the grain boundary discontinuous strip will be there. So, there will be some sort of a chance that if we really apply a load at much faster pace, still this the anti may fail under the brittle failures. And if we go ahead with slow loading, and then there will not be problem, it will be causing ductile failure. While in the case of the QT, the sample generally has a carbides abundance, which is the carbides are primarily distributed in a spherical discontinuity at the grain boundaries. In contrast to anti sample, carbides in the QT sample were largely dispersed at the borders or maybe the boundaries. So, this is what the difference comes when we are going through the different thermal cycles. Even though the base was the same, but we can change the properties. And now, why I have considered this as an example, reason being almost everybody has studied a steel and a steel formation, and we also seen what will be the residual stresses and the different level, and how the tempering is done to reduce those residual stresses, and that is why this example has been mentioned or maybe considered. Reason, if we have a familiar example or we understand the familiar example, then we can relate. Now, if any material, let us take copper, is exposed to the high temperature or is exposed to the high radiation, what will happen to those samples? Or in the polymers, if it is exposed to the environment which is having high temperature or even higher radiation. Now, what is the really meaning the temperature and radiation? Both have energy, and whenever the energy is being given to the material, naturally it will atomic level and molecular level, there will be some sort of change. Atoms will get energy and then they will get destabilized. To stabilize back, they either need to leave some sort of ion or maybe some sort of atom or maybe say some electron, and that will change the structure or that will change the properties. So, that is why we have considered this initial example as a steel example or the steel formation, so that understanding about the temperature influence on the metal on related property can be explained. Let us take now come to the radiation, and we often use the word the photochemical degradation. Now, reason being that we are going to talk about the photons, and whenever we talk about radiation, we generally express in terms of photons, because photons, those photons which have a high energy. We are not talking about lesser energy or negligible energy. So, we say substance exposed to the UV or maybe other radiation, it will these substances will absorb photons and which increase the energy of molecules. Once the energy of molecule increases, what happens to that? We know the stability, and then this curve has been picked up from a reference which has been also mentioned over here. So, what is in this case particularly, this is equilibrium point, stabilized point. Now, if photon has been absorbed by this atom, then what will happen? This will get destabilized and then it will leave maybe whatever the critical part and will come up and then escape. So, this photon energy exceed the escaping energy of the molecule or atom, and then finally we lose those atoms. And that has been shown here that even the high energy neutron or maybe say radiation have been imposed on the surface, we will be able to find some sort of dislocation, some sort of removal of the atoms from a matrix that will change the properties. So, this is mentioned. Now, here we are using the word photochemical, sometimes we use the word photoionization. The same thing happens, we say the atom dislodge and create a vacancy, and this vacancy will continuously increase and that will cause a void. And again, radiation exposure is not for a few seconds, it may be few minutes, few hours, few days. As more and more energy is given, naturally more and more weaknesses will be there and more chances of the failure will be there. So, this is we say that atom dislodge, create vacancy and create a void, and then there are chances also breakage of the covalent bond. We know very well every covalent bond has an energy, but if you exceed and you provide a more energy, and that extra energy can really break the bond, then the structure will change, and that is what has been mentioned over here, breakage of the covalent bond. Now, when a bond is broken, vacancy is created, what will happen? It is finally leading to the formation of the crack, which we have studied in the fatigue crack or the fatigue failure, the fatigue one, that cracks really, if that is the initial point, after the load, mechanical load is sufficient to grow those cracks, and then finally that will lead to the failure. Now, this has been mentioned here also, the crack maybe sufficient load has been applied or maybe some more and more energy is being given to that surface, then the crack will lead to the microstructure failure or the system failure or the surface failure in the manner. So, if I want to really express in other words what I mentioned here is that when it comes to the polymers, or maybe say polymers also there, because now one of the point in the polymer is that they do not have a high melting point. Even if you give a little bit energy, something like a 200 to 250 degree centigrade temperature, or maybe some sort of a radiation, what will happen? The bonds will break, and bonds will break, and quite possible there is a possibility of additional formation. So, that is why we use the word cross linking of the polymers. So, original will be getting maybe say broken, and then maybe if there are some other monomers available, they will start reacting with the parent polymer, and some new form of the polymer will come, which may be much weaker compared to the parent material or the parent material which we were using. And in this case also they go through the photochemical degradation. So, what finally comes out as a result, the strength and toughness of the polymer will decline. Another one which we said that the similar kind of process also may happen to the some sort of the dyes and pigments. What is the meaning of that? And what will happen, most of the time you have seen that because of the sunlight, things change a color, like maybe even the green color will be fade away slowly, or maybe yellow color will appear. So, this is what we say, the change in the pigment happens also, or maybe change in the color of the materials will happen, and then we need to really prevent it. Naturally, we require some good coating on the surface. Another one which we have studied something like photoionization, and then due to photoionization there is a possibility of the changing the electrical conductivity, because we will be losing some atoms. There will be some sort of effect on electrical conductivity, optical or mechanical properties. Those properties will change. And another one important point is that instead of the UV, if we go ahead with X-ray, then what will happen? X-ray will have a high energy photon which are effective to penetrate the material inside, induce ionization, and which will finally cause some sort of dislocation in the material. And such cases, if it is really happening to the metals, because the metals are very susceptible to the UV treatment, and because of that the brittleness will start. We will cover in this lecture a few examples how the brittleness will increase because of exposure to radiation. As the brittleness increases, naturally ductility will come down, and it will also cause some sort of a loss of the strength in this case. Now, if you think about the non-metal itself, non-metals, if there is a glass or ceramic, because they have a high melting temperature, they may not get affected that much with the radiation or maybe say a low temperature rise. However, if there is some sort of other polymers, or main thing is organic material, if the organic material, what will happen that this radiation will affect severely to those materials, and then we need to study it well in advance what will happen under different circumstances. So, either we should avoid those situations or we should avoid those materials. Now, we will come to the couple of examples on how it really affects radiation effects. So, this is the example which is the radiation effect on a metal and non-metal. This is a metal has been shown as a copper, and copper is very susceptible to the damage due to the radiation. And you can see here this is a microstructure, pretty smooth, while this microstructure enough cracks, enough the boundaries we are able to see, and it is really impacted severely. So, this is only exposure of the radiation with a time, and this is a common, particularly copper. That is why we say radiation reduces the ductility of the copper, it increases the brittleness of the copper, and by the dislodging atoms they change the atom location and create a number of vacancies. So, that is why we say this copper is subjected to embrittlement, that means increase in the brittleness of the surface. So, assume that the think about ductile is one of the very good ductile, copper is one of the very good ductile material, and it is just exposure of the radiation is changing its brittleness, maybe this microstructure to this kind of microstructure which has a many cracks. And that is what I mentioned earlier, by dislodging the atoms they generally start the chances of cracking, and that is what has been shown over here. Now, coming to the polymer, we have picked up this example from this reference. Now, this reference says what? You say there is some sort of polymer. Now, you expose this polymer to the radiation. What will happen? There will be some sort of discontinuity, or maybe some branches will be removed from this polymer, and in the presence of the other monomer, what will happen? There is a possibility of different chains to be formed on that, and that is what we are using the word grafted chains. This example has been shown with a microstructure in this manner. Now, this polymer has been shown, and without any radiation. Now, if this microstructure is exposed, or this sample is exposed to the radiation, we are able to see this kind of a structure, that is completely changing it microstructure, or completely affecting the microstructure in the radiations are affecting it, changing the complete behavior of the polymer in this manner. So, these are the important aspects, and then let us explore a couple of more examples. Polymer, now we are taking example of epoxy. We say this is another the good example, and it has been picked up from this literature. We are saying the UV radiation. You can see here the relatively smooth structure or microstructure in the beginning of the surface, that is what has been indicated A1. Now, if you keep for some time, maybe say around 250 hours, this has been mentioned here. So, if I keep this surface for the 250 hours, what will happen? We are able to see some sort of a nodules which is coming on a microstructure. That is also indication the surface degradation. Now, if you keep for some more times in something like a 500 hours, what is this has been shown, that is why the red color, you can see so many cracks, the way we have seen in copper surface exposed to the radiation, we are able to see so many cracks or so many the formation of the cracks over here. So many immediately within a 500 hours exposure, this kind of cracks are getting we say enhancing significantly, and after 800 hours what we find is a completely damaged crack have a deepen, and then maybe you can remove piece by piece all this. Of course, as I mentioned in the previous lecture, we should not remove the pieces. If you want the microstructure should be taken as it is in this form, so that we can understand properly. So, this is what we can say is a significant damage and of the epoxy, and the epoxy is does not have a very high melting temperature, and when it is really gets the radiation, naturally dislocation of the atom will occur, and then will cause some sort of a surface damage and the change in the surface behavior. So, maybe we can say here this was a ductile failure, and this has come to the, maybe it will be subjected to ductile failure, but this is a complete brittle failure, just exposure of the radiation. Now, this is a surface failure or microstructure failure, but this author also compared the property. You can see at the 0 hour the start, there are the tensile strength of epoxy itself was around 29 megapascal. After 250 hours, it has caused a decrease, maybe say roughly 5% decrease in this case, and then after 500 further decrease. Of course, in this case the surface has failed, but maybe the bulk material is still showing some sort of material strength, that is around 2/3 of earlier strength. Now, in this case toughness, which is again a core related thing, we are able to see the toughness initially was around 26.24 while it has come down to roughly 20. So, this is a core related, and what we are showing in this is surface related, and then the pull off strength, and sometimes we use the word shear strength also, that also comes down. So, all the properties are reducing with the time because of exposure of the epoxy to the radiation. So, what we can mention here, the long term exposure to the radiation degrades mechanical properties of epoxy. UV photons that are absorbed by the epoxy disrupt the chemical bonds, really excite the molecules and generate, main thing is the generate the free radicals. So, that chemical activity will also be on more side, and then it will cause a more and more damage. So, we need to keep in mind that UV radiation or maybe other kind of radiation are really harmful for the number of several materials. As I mentioned couple of examples, maybe ceramic or maybe glasses, there are few materials which will not get affected to a certain limit to the radiations. Now, let us cover the couple of more examples in this case. As you say that we are going to cover something like a stainless steel example, and then the stainless steel changes the behavior. The stainless steel changes the behavior from ductile behavior to the brittle behavior, just exposure on the time and the temperature, a combination. So, this is the temperature and this is the time dependence, and then we are going to we say that in covering one example which has been picked up from one of the reference. What they did, they made a number of pieces, a number of specimens, and then they exposed to the temperature 475 degree, which is a high temperature, and then but it's not and then they much lesser than the melting temperature of the stainless steel. Then what will happen, and they found microstructure maybe there is one sample which was ready, then they fractured that surface, and then after exposure to the 475 degree, they fracture the surface at the and they observe after 2 hours, they initiated the fracture and observed immediately. It is not that they have kept for the 2 hours, they immediately observed the fracture, and then they found the deep dimples in then the microstructure, and that is the indication that this kind of fracture is a ductile fracture. Even they did a similar kind of thing after 4 hours, and maybe say the sample was prepared initially, fractured, then exposed to the 475 degree for the 4 hours, and after that it was fractured, and then again they found that there is a deep dimples, and of course not as high density as after 2 hours, maybe that which is shown in A, but still this kind of fracture is a which is the ductile fracture. So, that is why we say in A and B we are able to find the deep dimples in a surface, and which is the indicative of the ductile failures. While coming to the 8 hours, then the sample was prepared, exposed to 475 degree for 8 hours, and after that it fractured, and we are able to find out some sort of the dimples also. There are some sort of the dimples also there, but there are some sort of the ridges also here. The ridge formation is also there in this case, and we are able to see that is an indication of the initiation of the brittle failure. And after 16 hours, what they find more and more points compared to the dimples, and density has reduced, the dimple density has reduced, and then this we can use the word a river pattern, and they find a more river pattern in this after 16 hours, and this causes more like a brittle failure. Of course, 32 hours and maybe say 64 hours, we are able to see many the cleavage in the failures are there in this case, cleavage failures are there, and that is indicative of what we say the brittle failure. So, this basically highlights that there is a relation between the embrittlement and microstructure. As the brittleness increases because of the time, even though in all the 6 cases the temperature is same 475 degree, but exposure was for 2 hours, 4 hours, 8 hours, 16 hours, 32 hours and 64 hours. In this case the brittleness, obviously the brittleness in this case is continuously increasing, and then this has a highest brittleness. So, this is important to consider, like if you are whatever the temperature you want, but how much time that temperature environment remain for the sample. If it is remain for 2 hours, 4 hours, 8 hours, 16 hours, naturally material behavior will be different. Even the surface which you are going to get after the fracture, that will be different, and that is our topic, that how the fracture will change with the time, how the fracture will change with the temperature, how the fracture will change with the radiation. Now, they also published in the hardness curve what has been mentioned here. This is what we are using the word aging time, the same thing in the number of hours, instead of that now they have put in number of minutes, and then they measure the hardness also. They are saying as age is the same temperature, sample is kept for the more and more time, interestingly their hardness is increasing. I assume initially that the hardness should come down, that the high temperature with the T and with a kind of a time it should decrease, because the creep behavior indicates that there will be more and more chances of failure. But here we are talking about the hardness, and then they have plotted that hardness will increase. Now, they have also given a justification, or they say the age significantly enhance the hardness of ferrite. So, there are two, maybe the stainless steel has a ferrite and austenite constitutes. So, austenite constitute keeps hardness same, while the ferrite hardness is continuously increasing. Now, as the ferrite hardness continuously increases, the embrittlement happens or brittleness increases, and then chances of the brittle failure will increase. So, what we can say with the time, ferrite phase becomes more and more fragile more and more prone to the brittle failure. And then as we have mentioned here, it shifts the microstructure shift from failure, the microstructure of the felt sample or surface shows a lesser dimple with the time, which is the shift from a dimple to the tearing rupture happens in this manner. So, this is what our aim was to introduce this topic, to show that how the temperature, how the radiations are affecting the materials, and I indicated that except the few materials, more large group of the materials are getting affected with the temperature or getting affected the radiation. And again I mentioned that I can go ahead with the individual analysis of the temperature or individual analysis of the radiation, or I can combine. Actually combined effect will be much more dominating, much more severe compared to the individual effect. So, this was the last slide of this lecture, and I will be covering, we will starting the corrosion topic, and then this is one of the extensive DEL topic, which is how the corrosion is affecting the surface degradation. And more interesting is that in presence of corrosion, even adhesion, abrasion, fatigue, everything changes. So, subsequent after 10th lecture we will be covering those topics also. Thank you for your attention.